So far, we've talked about acid additions to alkenes, and we used lots of different nucleophiles, but all of those went through a carbocation. Then we talked about halogenation in non-nucleophilic solvents and nucleophilic solvents. Then we moseyed on over to oxymercuration, demercuration, and we just finished covering hydroboration, oxidation. Whew, that was a lot. Let's hit a few more. Hydroboration oxidation is a syn addition reaction. You remember that, right? Yeah, hopefully. There are a few other syn addition reactions, so you can think about grouping these reactions we're learning in several different ways. And one of the ways that I think about grouping them is by similar mechanism. So the mechanisms we're about to go through are not necessarily similar to hydroboration oxidation, except that they all are syn addition mechanisms, syn addition products. Additionally, you might want to group them by what kind of transformation is happening, what kind of functional group you're making. We've made alkyl halides, that was acid additions to alkenes, but also halogenation. We've made alcohols, that was hydration of an alkene with acid and water, oxymercuration, demercuration, hydroboration, oxidation. You can categorize them a lot of different ways. These are some that I think about categorizing as oxidations and reductions. These two reactions are both oxidations, and this reaction is a reduction. So we're going to start out talking about hydrogenation, which is a reduction reaction. Let's do it. So this is hydrogenation. Hydrogenation turns an alkene into an alkane. It gets rid of a pi bond and adds two hydrogens in its place. I said previously that this is what I choose to teach next because it's also a syn addition product. So this one, we do not actually draw the mechanism for. It involves palladium. Palladium is definitely involved in this reaction, but it's a transition metal, and we, at this level of organic, don't really draw transition metal mechanisms. They're different from a lot of the mechanisms we will see, but in higher level chemistries or in organometallics class, we'll definitely draw mechanisms with transition metals. Okay, so palladium, this could also be platinum or even nickel. All of those are upstairs, downstairs neighbors on the periodic table. Check them out. We have a solid palladium, a solid platinum, a solid nickel surface. I've drawn it like a big block of palladium platinum. It's not. It's little tiny granules most of the time, but we have a solid surface of palladium, and we add hydrogen gas to the mixture as well. So solid surface, hydrogen gas. The hydrogen gas adsorbs, with a D, adsorbs to the surface of the palladium, and it's kind of like there's a bunch of lollipop hydrogens hanging off the palladium. Is it really lollipop hydrogens hanging off? No, not at all. But it's kind of like there are lollipop hydrogens hanging off the surface of the palladium, of the solid metal of choice, palladium, platinum, nickel, whatever. There's lollipop hydrogens hanging off, and what happens is an alkene hovers over those little lollipop hydrogens. Why am I drawing the alkene like this with dashes and wedges on it instead of like that? Well, the pi bond, remember, spans above and below the plane of the molecule. The 6 atoms, the 6 carbon atoms, are all in the same plane, but the pi bond is orthogonal to that plane. The pi bond is not in the same plane as the 6 atoms. So we turn the alkene sideways so that the pi bond can hover over the lollipop hydrogens. Why is it good for the alkene to hover over the lollipop hydrogens? Because this is not exactly how it happens, but we're going to draw it like that. We're going to draw it like it's a little concerted mechanism, where what happened was a hydrogen was attacked by this carbon on the left. That hydrogen gave up his electrons to palladium metal, and this hydrogen took his electrons and attacked the other carbon of my alkene over there. So what I ended up with was 2 hydrogens simultaneously getting stuck to, hooking up with that alkene. My pi bond broke, and I got a single bond in the middle, an alkane in the middle, and both hydrogens jumped on simultaneously. What's the fancy word for simultaneously? Concerted. And all concerted reactions give you syn stereochemistry. So there it is. Is this a mechanism you have to know? No, because what we drew is not even a legit mechanism. It's a little bit fabricated, but it's kind of how it works, a little bit. This reaction is very exothermic. That means it releases a lot of heat as this hydrogenation takes place. We're going to use that to talk about some alkene stability in one moment, but I just want to point out again that the stereochemistry of this reaction is syn because it was a concerted process. Two H's got added to the same side. Does that make any difference in this specific example? No, not one bit. The H's got added, but I didn't make an asymmetric carbon here. I didn't make an asymmetric carbon there, so it didn't matter. But it's going to matter. But first, let's talk about this exothermic bit. There are lots of different varieties of alkenes, as in lots of different substitution patterns of alkenes. I'm drawing a few of them for you over here. All of these alkenes have different substitution patterns. What do I care about it? Well, this alkene, this top one, this ethene, we would call an unsubstituted alkene. The next one in line we would call a monosubstituted alkene. Then comes a disubstituted alkene, and oh look, another di, and a di, and a di, and then a tri, and then a tetra. What that's saying is how many groups that are not hydrogen are connected to the alkene. A tetrasubstituted has 4 groups that are not hydrogen connected to the alkene. A tri-substituted has 3 groups that are not hydrogen connected to the alkene. Okay, I have drawn these in order of stability. What? How do you know? Well, in order to measure stability, we can talk about heats of hydrogenation. The way to read this plot is things on higher energy shelves are less stable. It's always more stable to be on a low energy shelf. So ethene, this is unsubstituted alkene over here. Ethene is the least stable of these alkenes. Then came a monosubstituted. Then came a di that's cis. Then a di that's trans, and a di where the two substituents are on the same side, so it's not E or Z. It's not cis or trans. Yeah, that's the same stability. Then came tri, and then came tetra. Tetra is the most stable alkene because it has the lowest, smallest heat of hydrogenation. Okay, so I borrowed this from down here, and they say that these numerical data they have presented are all from the carbon-6 series, but the general trend is the same no matter how many carbons you have in your molecule. More substitutions leads to more stable products. Okay, that was enough of a hiatus. Let's go back to hydrogenation and specific stereochemistry of hydrogenation. So I've said that reaction is syn addition. Note, these use platinum instead of palladium. It don't matter. It's the same thing. Imagine there were lollipop hydrogens, and our little alkene hovered over those lollipop hydrogens, and we picked up 2 hydrogens added on the same side, like so. We get this product. That's if it hovered with this bottom face, the face pointed down here. That's if this bottom face is what hovered over the surface. What if this top face hovered over the surface? Remember, it's not really a solid surface like a table. It's little granules that are all being stirred in solution together. So it's very easy for the solid surface to come in contact with what's called the top face, or what we would think of as the top face here. What do you get there? Well, you get this. You get your 2 hydrogens pointed straight up instead of straight down. But the methyl and deuterium stay in the same respective spots, as in methyl pointed away and deuterium pointed toward on the rightmost carbon, and the opposite on the leftmost carbon. Okay. So So I probably have more to say about that reaction, but I want to say it in comparison to the bottom version. So let's draw the product of the bottom version as well. Two hydrogens pointed straight down, the methyls stay coming towards you, the deuteriums stay going away. Methyl over here, methyl over there. That's if it hovered with kind of the bottom face over the solid support. What if the top face were hovering over the solid support? We get this. And I say, something's interesting about these two reactions. What is it? Well, this, I see a plane of symmetry right here. Do you? Yeah, hopefully you do. What does that mean? Is this an asymmetric carbon? Yep. Is that an asymmetric carbon? Yep. Is there a mirror plane going down the middle of that molecule? Yep. So since that's the case, that means that this bottom reaction does not create these two products. It creates only one product, only this product, because that product is meso. The top one does not create a meso product because if I align it the way that it is, where the two hydrogens are aligned, the methyl and deuterium reflect back to each other. That's not. Methyl and deuterium. I don't have a mirror plane in these top ones. I can rotate it if I wanted to, but I'm not ever going to rotate it in a way that's going to show me a mirror plane, because there's not one. So you may think it's kind of weird that we chose to draw our alkenes this way instead of in a planar perspective, and admittedly it is kind of weird, especially at first. But one of the main reasons for drawing it in this perspective, where the dashes and wedges are shown around an alkene instead of that perspective, is when you point two things in the plane straight up or straight down, straight up or straight down, and you keep the exteriors, the dashes and wedges things, the same orientation that they were in previously, it's an easy way to guarantee that you're going to get your stereochemistry right. This conformation is an eclipsed conformation. In an eclipsed conformation like this, my two H's are syn. If I were to unravel this and put it in a planar perspective, let's do that up above. Let's put it in a normal zigzag planar perspective like that. Well, if I rotate this right carbon so that my methyl is now going to be pointed up, but in the plane, that's like a 60-degree tick, like a little Newman projection, 60 degrees, methyl is going to go up and in the plane. And I have two things pointed down below, in and out of the plane. Methyl comes forward a 60-degree tick. That's going to push deuterium a 60-degree tick, but it's actually still coming out toward you. That pushes hydrogen a 60-degree tick to back behind the plane. All I did was rotate a tiny little fraction around this asymmetric carbon. What if I rotate a tiny little fraction around that asymmetric carbon? This methyl, I'm pushing backwards a tiny little tick to be in the plane now. That's going to bring my deuterium forward, and it's going to push my hydrogen backwards. Would you have been able to look at this projection, this perspective, and see that those two hydrogens had been added syn? Well, they're both dashed, so maybe, but the problem is rotation can happen around that single bond without getting down in the rabbit hole too deep. What if I rotate around that central bond now, and I'm going to rotate the rightmost carbon? I really don't have much room up here. Okay, So I'm going to keep my rightmost carbon in the exact same perspective as previous in the purple structure over there. Rightmost, that's left. Leftmost carbon stays the same. Rightmost carbon, I'm rotating 180 degrees. 180 degrees puts my deuterium in the back, and it puts my hydrogen in the front. Could you look at this projection, this perspective, this blue thing, and tell that those hydrogens were added syn? No. They're pointed opposite directions. So it looks like they were not added syn. Okay, pause. If you got nothing else out of that whole discussion I just had, here's the take-home message. I started out with an alkene that cannot rotate. I added 2 hydrogens to make a single bond that can rotate. So once I have a single bond, I can draw my product in this kind of perspective that's eclipsed, this kind of perspective that's staggered, or even this kind of perspective that's eclipsed. And all of those are identical products. Go back and assign R's and S's to prove it to yourself if you need to. All 3 of those are identical products. So be careful, just because these H's don't look syn right here, doesn't mean they weren't added syn. They were added syn, but the rotation around that central bond causes the final product to look different. Okay? Alkenes can't rotate. Single bonds can. You can draw the products in a lot of different perspectives. All right, we're sticking a fork in that. The last thing I want to point out before we get away from here, the top 2 products, definitely 2 different products. The relationship between them is that they are enantiomers. We would make a racemic mixture of enantiomers up here. Bottom product, this is the one and only product that's created because it's a meso compound. The end. So we said hydrogenation happens on a solid surface. The alkene has to hover near a solid surface. Something like this that has an alkene, from the top, it's sterically hindered. The solid surface, the palladium, the platinum, the nickel, the solid surface cannot easily access the top face of the alkene down here because the methyl up there is kind of blocking it. The bottom face is totally open and ready for approach from the solid support, the platinum, the palladium, the nickel, the stuff. So this product on the left, my laser's not showing up, this product on the left has my 2 hydrogens added syn, and they came in from the bottom face. This product on the right has my H's added syn, but they have to have come from the top face. That cannot happen because of steric stuff in this molecule, so this particular example makes the left product and only the left product. But I give you this as a very small side nugget example that says usually when hydrogen's added, it's added to the top face and the bottom face, and you might get a racemic mixture out of that. That is if you don't make a meso compound. Watch out for mesos. So that last reaction was hydrogenation of an alkene. What about hydrogenation of an alkyne? Can we do that? Yeah, absolutely, we can do that. It's a concerted thing, happens all together. You're going to get syn addition, and you get 2 H's added syn, like that. This would be called a cis double bond, a Z double bond. That's what you get out of it. But. You cannot control the number of equivalents of this thing, as in, when you add hydrogen and platinum to an alkyne, it makes an alkene, this cis alkene, this Z alkene, but it doesn't stop there. It cannot stop there. In the end, you reduce all the way to an alkane. There are no more pi bonds to be taken away. It does go through an alkene, but it does not stop at an alkene, goes all the way to an alkane. Hydrogenation of an alkyne produces an alkane. Okay. Well, there's more to the story. Of course, always. There's always more to the story. H2 and Lindlar's catalyst. Lindlar's catalyst is a palladium compound that has been poisoned. It has been made less active. Sometimes it's poisoned with something like calcium carbonate. Lindlar's catalyst is a very specific recipe of what it's poisoned with. So the point of the poison is that the catalyst, as in the metal, has become less activated. It's less reactive now. So in H2 and Lindlar's catalyst, you make an alkene through a syn addition, just like the one we've talked about that does kind of a lollipop hydrogen mechanism. It does a syn addition to get you a cis alkene, and it stops. It's done. Stick a fork in it, no more product, no more reduction, it's done. Regular hydrogenation, you cannot stop at an alkene. You continue from an alkene to an alkane. Hydrogenation with Lindlar's catalyst, because Lindlar's catalyst has been poisoned and made less reactive, stop at a cis alkene. Okay, alkyne reduction. We can turn an alkyne into an alkane. We can turn an alkyne into an alkene, but a cis alkene. We can turn an alkyne into an alkene, but a trans alkene. That's what this bottom one is doing. A trans alkene. We're not going to draw the mechanism for how to make this trans alkene. It is in your textbook and is something that you could take a look at, but we're not going to draw it, how it happens. It's called the dissolving metal reaction. The reason it's called that is because this is solid sodium metal. Like metal, if you pull up a YouTube video, metal that you dump in the lake and look it up. Solid sodium metal and liquid ammonia. So you dissolve that metal into liquid ammonia-ish, and it goes through a reaction in order to do some single electron transfers, some weird kind of stuff going on in this thing. But the take-home message, what you need to know is alkyne plus metal and ammonia gives you a trans alkene. It could be sodium, it could be lithium. We will most often see sodium, but it really could be another neighbor of sodiums. Alkyne plus metal and ammonia, you get a trans alkene. This is hydrogenation of an alkyne, which is different from hydrogenation of an alkene. The first problem, the first reaction up here, is in common with an alkene, but the bottom two are specific to alkynes and alkynes only. Alkenes don't do these bottom reactions because you end up making alkenes. You can't go any further. While we're talking about alkynes, well, let's see some more reactions that they do. Well, let's actually start with the middle reaction here and see what should this middle reaction do. Br2. I've seen that before. Alkene attacks Br. That's alkyne. Alkyne pi bond attacks Br. Br attacks back. This other Br leaves. It's going to make a bromonium. A bromonium of an alkyne looks like this. Boy, that's weird. Bromide. Bust open that bromonium. Either side is equally substituted, so it don't matter. I end up with a bromine here and a bromine there because halogenation does anti-addition. When you bust open that bromine, you got to invert that stereocenter. So we end up with the E alkene and only the E alkene in that example. Yep. I'm going to make myself a tiny bit more room for the top reaction because now it's time to talk about it. We've got BrCl. What? BrCl. Yeah, it's a mixture. It's a compound that has a Br and a Cl. Is it a polar compound? Yes. Pulling electrons toward the chlorine. So who's most likely to get attacked by my alkyne? Bromine. Alkyne attacks the bromine because bromine is more electropositive. Bromine has fewer electrons because there's a dipole pointed toward chlorine because he's more electronegative. So bromine attacks back. Why did it attack that carbon back? Because that carbon has better carbocation character. That carbon has is a secondary carbon, while the other is a primary carbon. There we go. So I make a bromonium, and then I'm ready to bust it open. Who comes to bust it open this time? Water. Water comes to bust it open. And I'm not going to draw the full mechanism steps because you know what they are, what they should be. Br is up here. Methyl got booted up there. I end up with OH there. But, oh boy, let's see who's really paying attention. Oh boy. I have an alkene and an alcohol on the very same carbon. An alkene and an alcohol on the very same carbon. That's an enol, and that enol will, what's that word? Tautomerize. That enol will tautomerize to become, oh my, this ketone. Oh boy. Yeah. We'll draw a tautomerization step one day, but not quite yet. You can look it up in your textbook in the meantime. All right, on to the bottom reaction. We react our alkyne with 9-dBn. Remember, 9-dBn is that banana borane thing, but it's really just BH3, but really big. Okay, so after the 9-dBn reacts, we end up with hydrogen added here, and boron added there. We're going to say Br2. Is that all right with you? It's not a Br as in bromine, a B with R's as in carbon R's. Yeah. That's what happens after this first step. And then I add hydroxide and peroxide. That does a replacement, replacing the boron with an OH, and everybody else stays the same. Note, the way I have drawn this alkene, the way I've drawn my product, the H and the OH got added to the same side. But this is not my final product. Let me see if you can figure out why this is not my final product. Any ideas? Thoughts? Ideas? Thoughts? That enol will tautomerize to make this aldehyde as a final product. We will draw a tautomerization later. I promise we will. But I guess I should say a little something more about it. These two things, the relationship between those two things is that they are tautomers of each other. Tautomers are things that differ by the placement of one pi bond and one hydrogen. This hydrogen up here that's on the oxygen ends up connected to the carbon next door. The pi bond that was making the carbon-carbon pi bond, that becomes a COO pi bond. So your C-double-C and OH changes into a COO and an extra H on my carbon. We will draw a tautomerization mechanism later. I'm just not ready for it right now. Okay. So in this video so far, we have done hydrogenation, and then we've recapped some alkyne reactions that we had already talked about with alkenes. All right, next comes hydroxylation. Hydroxylation is alkene reacts with cold dilute KMnO4, and you get two OHs that are syn. Remember, we're categorizing these as syn addition reactions. Two OHs that are syn and MnO2. This reaction is known as a qual test, like a previous reaction we've talked about was a qual test. It's often a color change, some apparent change to signify did I have this functional group or not. KMnO4 is a purple solution, a purple compound. When you react this purple KMnO4 with an alkene, it ends up making a brown precipitate, MnO2, manganese dioxide. That's not true. Manganese 4 oxide. This KMnO4 is called potassium permanganate. Potassium permanganate is the purple stuff. Potassium permanganate is a strong oxidizing agent. That means it's good at helping to oxidize other things. It's so good at oxidizing, sometimes it actually over-oxidizes alkenes. We'll talk about over-oxidizing a few slides from now, but potassium permanganate is a good oxidizing agent. One reason that this really needs to be cold and dilute is to try to calm him down and keep him from over-oxidizing. So sometimes reagent details are not super important, but KMnO4 cold dilute does something very different from KMnO4 that's hot and refluxing. So this cold dilute is unfortunately a necessity when you're writing reagents down. So since sometimes potassium permanganate gets a little over-vigorous, a little overzealous, we can use osmium tetroxide because osmium tetroxide is a kinder and gentler oxidizing agent. It makes an intermediate like this. That intermediate can then be oxidized to become this product, these products. We jumped ahead a lot of steps. Let me back up a minute. The mechanism of how potassium permanganate works is not something we need to be fully aware of because what I'm about to draw is not a complete mechanism. But potassium permanganate, you got permanganate with a little negative charge and potassium floating off because it's an ionic thing. MnO4, manganese is a big transition metal. We are greatly exceeding its octet right here, but it's a big old guy. It's fine. It's a transition metal. The mechanism kind of goes something like this-ish to make an intermediate like this. The reason I kind of point out that mechanism is because I want to point out that there are three arrows happening all at once right here. That first step is concerted. What does it mean to be concerted? Happening all at once. And anytime something's happening all at once with an alkene that is trigonal planar, it has to be happening on one face or the other, which is going to lead to certain stereochemistry in your product over there. It's going to lead to syn addition. That's syn with your OHs coming forward, or syn with your OHs going backwards. So you get this cyclic intermediate that goes through further oxidation. Sometimes I say it's magic. Whoa, oh, it's magic. Yeah, what happens next is not something that we will discuss, but what happens next is the manganese goes away, becomes MnO2, and the O's split from the manganese and become OHs. We won't worry about how, but the take-home message is syn addition because this first step is concerted. Okay, back to where we were. Osmium tetroxide does the same dang thing. Osmium looks a heck of a lot like manganese, but it's in a different group of the periodic table. It's not an ionic thing, so we've got all double bonds all around that osmium instead of mostly double with one single. But it happens a lot the same as the other. We're going to attack one of those. One of those is going to attack back. It's concerted a little bit down there to make this cyclic intermediate. That cyclic intermediate needs some hydrogen peroxide to further oxidize and end up with my two products presented there. Wait, why are these two products presented as they are? If I had designated this methyl as a wedge in the beginning, I still end up with my two OHs syn. My two OHs syn. But they are, those being syn does not change the stereochemistry of the neighboring carbon. The reaction did not happen at this carbon, therefore this carbon does not get affected. So, are these molecules enantiomers? No, they're diastereomers, because the carbon where the methyl is was there in the beginning and it was not affected. Reaction didn't happen there. The two circled OHs are what we added, and they must be syn but they don't have to be syn to the methyl. Maybe that makes sense? I think I've said enough about it. All right, so we've done hydrogenation and hydroxylation. It's time for oxidation with a peroxy acid. That was a mouthful. It's about time we ask the question, what is an oxidation? In a general chemistry definition, it's loss of electrons. Oxidation is loss of electrons. In an organic definition, it's still the same thing, but we just tweak our definition a little bit to talk more about bonds, because organic is all about bonds. In organic, we say making bonds to oxygen is called an oxidation. We also say making bonds to hydrogen is a reduction. We also say breaking bonds to oxygen is a reduction, and breaking bonds to hydrogen is an oxidation. I think maybe that's worth me repeating, even though you can rewind. We say making bonds to oxygen is oxidation. And making bonds to hydrogen is reduction. We say breaking bonds to oxygen, reduction, and breaking bonds to hydrogen is an oxidation. Hopefully you followed my words, because we know my handwriting is not legible. Okay, so this reaction is going to be an oxidation. If you go back and look, dihydroxylation, that's also an oxidation reaction. Flip back one more page, the hydrogenation, that's a reduction reaction. So this is an oxidation, so was hydroxylation, and hydrogenation was reduction. Whew, yeah, okay. The mechanism, the way it works. Alkene attacks oxygen. Why that oxygen? Well, we've said before that peroxide bonds are not terribly stable. So we actually have a lot of things that happen all at once here. This is not quite all yet. Alkene attacks oxygen. Oxygen's ready to lose some of its electrons, so oxygen loses that OO single bond because that's really a not stable bond anyway. Then I break this CO pi bond to grab onto this H that was just going to be lost in space. And so those electrons that were holding onto that H have to go somewhere, and they attack a carbon. And you say, skirt, what? 4 little arrows all at once. That is a crazy, chaotic mess. Do you really expect me to know that? Well, I think it's helpful to explain why reactions do what they do sometimes, but this one is a wackadoodle mechanism for sure. The red oxygen is now a red oxygen in a 3-membered ring with an oxygen in it. That oxygen does not have a plus charge, so yeah, but a 3-membered ring with an oxygen in it. I made this as my side product. This is a carboxylic acid. And this molecule is an epoxide. Epoxides are important in future chemistries that we're going to do, but for now, you need to know how to make them as well. This reagent that we added has an R group. It's not real specific, but this reagent that we added is called RCO3H. It's a peroxy acid. Peroxy acid means it's kind of like a peroxide. It's kind of like a carboxylic acid. It's a combination of the two. It's a peroxy acid. Peroxide, OO, single bond. Carboxylic acid, COOH. Meh, this one just has an extra O squizzed in the middle. One of our very favorite specific peroxy acids is this one. That's benzene with a peroxy acid connected to it, and a chlorine over there 2 carbons away down here. The chlorine down there doesn't really matter, but this thing is so famous that he has an acronym. His acronym is MCPBA because his name is really long. His name is metachloroperoxybenzoic acid. He's one of the most famous carboxylic acids, one of the most famous peroxy acids, because he's a solid at room temperature, and he's a pretty stable peroxy acid. A lot of other peroxy acids not so stable. So MCPBA, if you see an alkene with an arrow with MCPBA over it, you need to know MCPBA is a peroxy acid, and peroxy acids turn alkenes into epoxides. Yeah? Okay. So that wraps up syn additions. There's one more oxidation reaction we're going to talk about, but let's tack it on a different video so that we can categorize this whole thing as syn addition reactions. Oh, actually, as I say that, I just realized I did not actually draw this guy as syn. Oh, silly me. That's 4 arrows happening all at once. Hopefully you recognize that thing's concerted, and anytime a reaction is concerted, you get syn stereochemistry. This is a meso product, so I don't have to worry about a pair of enantiomers being created. Oh man, okay, let's really end this video because it's long enough and it's all the syn additions all in one video. Done.